how smart connected products are transforming companies. Smart everything from the smartphones to smart everything under the business management. The evolution of products into intelligent connected devices, which are increasingly embedded in broader systems, is radically reshaping companies and competition. Smart thermostats control a growing array of home devices, transmitting data about their use back to manufacturers. Intelligent networked industrial machines autonomously coordinate and optimize work. Cars stream data about their operation, location, and environment to their makers and receive software upgrades that enhance their performance or head off problems before they occur. Products continue to evolve long after entering service. The relationship a firm has with its products and with its customers is becoming continuous and open ended. In our previous HBR article, How Smart Connected Products Are Transforming Competition, we examined the implications external to the firm, looking in detail at how smart connected products affect rivalry, industry structure, industry boundaries, and strategy. In this article, we will explore their internal implications, how the nature of smart, connected products substantially changes the work of virtually every function within the manufacturing firm. The core functions products development, IT manufacturing, logistics, marketing, sales, and after sales service are being redefined, and the intensity of coordination among them is increasing. Entirely new functions are emerging, including those to manage the staggering quantities of data now available. All of this has major implications for the classic organizational structure of manufacturers. What is underway is perhaps the most substantial change in the manufacturing firm since the second industrial revolution more than a century ago. Implications for strategy, the new product capabilities. To fully grasp how smart connected products are changing how companies work, we must first understand their inherent components, technology, technology and capabilities, something that a previous article examined. To recap, all smart connected products from home appliances to industrial equipment share three core elements: physical components such as mechanical, electrical parts, and the smart components, sensors, microprocessors, data storage, controls, software, an embedded operating system, and a digital user interface. And connectivity components, ports, antenna, protocols, and networks that enable communication between the product and the product cloud, which runs on remote servers and contains the product's external operating system. Smart connected products require a whole new supporting technology infrastructure. This technology stack provides a gateway for data exchange between the product and the user, integrates data from business systems, external sources, and other related products. The technology stack also serves as the platform for data storage and analytics, runs applications, and safeguards access to products and the data flowing to and from them. The new technology stack. Smart connected products require companies to build and support an entirely new technology infrastructure. This technology stack is made up of multiple layers, including new product hardware, embedded software, connectivity, a product cloud consisting of software running on remote servers, a suite of security tools, a gateway for external information sources, and integration with enterprise business systems. This infrastructure enables extraordinary new product capabilities. First, products can monitor and report on their own condition and environment, helping to generate previously unavailable insights into their performance and use. Second, complex product operations can be controlled by the users through numerous remote access options. That gives users the unprecedented ability to customize the function, performance, and interface of products and to operate them in hazardous or hard to reach environments. Thirdly, the combination of monitoring data and remote control capabilities creates new opportunities for optimization. Algorithms can substantially improve product performance, utilization, and uptime, and how products work with related products in broader systems such as smart buildings and smart farms. Fourth, the combination of monitoring data, remote control, and optimization algorithms allow autonomy. Products can learn, adapt to the environment and the user preferences, service themselves, and operate on their own. Reshaping the manufacturing company. To create products and get them to customers, manufacturers perform a wide range of activities which generally take place in a standard set of functional units. Research and development are engineering, IT, manufacturing, logistics, marketing, sales, after sales service, human resources, procurement, and finance. The new capabilities of smart connected products alter every activity in this value chain. At the core of what is reshaping the value chain is data. The new data resource. Before products became smart and connected, data was generated primarily by internal operations and through transactions across the value chain. Order processing, interactions with suppliers, sales interactions, customer service visits, and so on. Firms supplemented that data with information gathered from surveys, research, and other external sources. By combining the data, companies knew something about customers' demand and costs, but much less about the functioning of products. The responsibility for defining and analyzing data tended to be decentralized within functions and siloed. Though functions shared data, sales data, for example, might be used to manage service parts inventory. They did so on a limited episodic basis. Now, for the first time, these traditional sources of data are being supplemented by another source, the product itself. Smart connected products can generate real-time readings that are unprecedented in their variety and volume. Data now stands on par with people, technology, and capital as a core asset of the corporation, and in many businesses is perhaps becoming the decisive asset. This new product data is valuable by itself, yet its value increases exponentially when it is integrated with other data, such as service histories, inventory locations, commodity prices, and traffic patterns. In a farm setting, data from humidity sensors can be combined with weather forecasts to optimize irrigation equipment and reduce water use. In fleets of vehicles, information about the pending service needs of each car or truck and its location allows service departments to stage parts, schedule maintenance, and increase the efficiency of repairs. Data on warranty status becomes more valuable when combined with data on product use and performance. Knowing that a customer's heavy use of a product is likely to result in premature failure covered under warranty, for example, can trigger preemptive service that may preclude later costly repairs. Smart connected products require a rethinking of design. Data analytics, as the ability to unlock the full value of data, becomes a key source of competitive advantage. The management, governance, analysis, and security of that data is developing into a major new business function. While individual sensor readings are valuable, companies often can unearth powerful insights by identifying patterns in thousands of readings from many products over time. For example, information from disparate individual sensors such as the car engine temperature, throttle position, and fuel consumption can reveal how performance correlates with the car's engineering specifications. Linking combinations of readings to the occurrence of problems can be useful, and even when the root cause of a problem is hard to deduce, those patterns can be acted on, and data from the sensors that measure heat and vibration, for example, can predict an impending bearing failure days or weeks in advance. Capturing such insights in the domain of big data analytics, which blend mathematics, computer science, and business analysis techniques. Big data analytics employ a family of new techniques to understand those patterns. A challenge is that the data from smart, connected products and related internal and external data are often unstructured. They may be in an array of formats such as sensor readings, locations, temperatures, and sales and warranty history. Conventional approaches to data aggregation and analysis, such as spreadsheets and database tables, are ill suited to managing a wide variety of data formats. The emerging solution is a data lake, a repository in which disparate data streams can be stored in their native formats. From there, the data can be studied with a set of new data analytics tools. Those tools fall into four categories: descriptive, diagnostic, predictive, and prescriptive. These are the data sources enterprise smart connected products with the external data on prices. Data lake include the analytics including the descriptive, diagnostic, predictive, and prescriptive, all leading to business, customer, and partner. To better understand the rich data generated by smart connected products, companies are also beginning to deploy a tool called a digital twin. Originally conceived by the Defense Advanced Research Projects Agency DARPA, a digital twin is a 3D virtual reality replica of a physical product. As data streams in the twin evolves to reflect how the physical product has been altered and used and environmental conditions to which it has been exposed. Like an avatar for the actual product, the digital twin allows the company to visualize the status and condition of a product that can be thousands of miles away. Digital twins may also provide new insights into how products can be better designed, manufactured, operated, and serviced. Transforming the value chain. The powerful new data available to companies, together with new configurations and capabilities of smart, connected products, is restructuring the traditional functions of business, sometimes radically. This transformation started with product development but is playing out across the value chain. As it spreads, functional boundaries are shifting and new functions are being created. Product development. Smart connected products require a fundamental rethinking of design. आज आवा है. Transforming the value chain, the powerful new data available to companies, together with new configurations and capabilities of smart, connected products, is restructuring the traditional functions of business, sometimes radically. This transformation started with product development but is playing out across the value chain. As it spreads, functional boundaries are shifting and new functions are being created. Product development. Smart connected products require a fundamental rethinking of design. At the most basic level, product development shifts from largely mechanical engineering to true interdisciplinary systems engineering. Products have become complex systems that contain software and may have as much or more software in the cloud. That's why design teams are shifting from a majority of mechanical engineers to the majority of software engineers, and some manufacturers like GE, Airbus, and Danaher are establishing offices in software engineering hubs like Boston and Silicon Valley. Smart connected products also call for product design principles that depart dramatically from tradition. Low cost variability. In conventional products, variability is low costly because it requires variation in physical parts. But the software is in smart, connected products makes variability far cheaper. For example, John Deere used to manufacture multiple versions of engines, each providing a different level of horsepower. It now can alter the horsepower of a standard physical engine using software alone. Low cost variability. Variability is needed not only across customer segments but also across geographies. Software also makes it easier to localize products for different countries and languages. However, emerging local regulations for data standards, such as those governing the transmission of data across national boundaries, require duplication of data storage infrastructure or applications. Such regulations are introducing new country and regional differences, sometimes for political reasons. Evergreen design. In the old model, products were designed in discrete generations. The new product incorporated a full set of desired improvements and the design was then fixed until the next generation. Smart connected products, however, can be continually upgraded via software, often remotely. Products also can be fine tuned to meet new customer requirements or solve performance issues. The performance of ABB robotics industrial machines, for example, can be remotely monitored and adjusted by end users during operation. Companies can release new features that are works in process, not finalized. Recently, Tesla began putting an autopilot system in its cars, but with the intention of enhancing the system's capabilities over time through remote software updates. New user interfaces and augmented reality. The digital user interface of a smart connected product can be put into a tablet or smartphone application, enabling remote operation and even eliminating the need for controls in the product itself. As noted, these interfaces are less costly to implement and easier to modify than physical controls, and they enable greater operator mobility. Manufacturing goes beyond production of the physical object. some products have begun incorporating a powerful new interface technology called augmented reality through a smartphone or tablet pointed at the product or through smart glasses. Augmented reality applications tap into the product cloud and generate a digital overlay of the product. This overlay contains monitoring, operating, and service information that makes supporting or servicing the product more efficient. Constructing these powerful digital interfaces is another critical new design discipline. Ongoing quality management testing that tries to replicate conditions in which the customer will use products has long been part of product development. The aim is to ensure that new offerings will live up to their specifications and to minimize warranty claims. Smart connected products take quality management several steps further, enabling continuous monitoring of real world performance data, allowing companies to identify and address design problems that testing failed to expose. In 2013, for example, batteries in two Tesla Model S cars were punctured and caught fire after drivers struck metal objects in the road. The road conditions and speeds leading to the punctures had not been simulated in testing, but Tesla was able to reconstruct them. The company then sent a software update to all vehicles that would raise their suspension under those conditions, significantly reducing the chances of further punctures. Connected service product designs now need to incorporate additional instrumentation, data collection capability, and diagnostic software features that monitor product health and performance and warn service personnel of failures. And as software increases functionality, products can be designed to allow more remote service. Support for new business models, smart connected products let companies switch from transactional selling to product as a service models. However, this shift has product design implications. When a product is delivered as a service, the responsibility for and associated cost of maintenance remain with the manufacturer, and that can alter several design parameters. This is especially true when multiple customers share the product, as is the case at Smooth, a bike sharing service in France. Smooth has designed its smart connected bikes with chainless drive shafts, puncture-resistant tires, and anti-vandal nuts to improve durability and prevent theft. Products delivered as services must also capture usage data so that customers are appropriately charged. This requires clear thinking about the type and location of the sensors, what data will be gathered, and how often it should be analyzed. And Xerox evolved from selling copiers to charging by the document. It added sensors on the photoreceptor drum, feeder output tray, and toner cartridge to enable accurate billing and facilitate the sale of consumables like paper and toner. System interoperability. As products become components of broader systems, the opportunities for design optimization multiply. Through code design, companies can simultaneously develop and enhance hardware and software across a family of products, including those of other companies. Take Nest Labs self-learning thermostat. It was designed with an application programming interface that allows it to exchange information with other products, such as Kivo's smart lock. When the homeowner enters the house, the Kivo lock communicates that to the Nest thermostat, which then adjusts the temperature to the homeowner's preference. Manufacturing smart connected products create new production requirements and opportunities. They may even shift final assembly to the customer site, but the last step is loading and configuring software. But more radical still, manufacturing now goes beyond the production of the physical object because a functioning smart connected product requires a cloud-based system for operating it throughout its life. Smart factories. The new capabilities of smart connected machines are reshaping the operations of manufacturing plants themselves. where machines increasingly can be linked together in systems. In new initiatives like Industry 4.0 in Germany and smart manufacturing in the United States, networked machines fully automate and optimize production. For example, a production machine can detect a potentially dangerous malfunction, shut down other equipment that could be damaged, and direct maintenance staff to the problem. These brilliant factories initiatives uses sensors to stream information into a data lake where it can be analyzed for insights on cutting down time and improving efficiency. In one plant, this approach doubled the production of defect-free units. Simplified components, the physical complexity of products often diminishes as functionality moves from mechanical parts to software. This shift eliminates physical components along with the production steps needed to build and assemble them. Withings, for example, has reduced its blood pressure monitor to a cuff and sensor, eliminating the display through an app that can track blood pressure and send updates directly to the clinicians. Similarly, manufacturers of aircraft, automobiles, and boats are moving toward glass cockpits in which a single screen displays numerous configurable gauges. As the physical complexity of products decreases, however, the quantity of sensors and software rises, introducing new parts and complexity.